Thank you very much, Rishi, for the invitation, first of all, and also for the kind introduction. So I will talk about the calculation of hadronic contributions to the G-2. Here's the outline. There will be two main chapters, hadronic vacuum polarization and hadronic light by light, which are the two main sources of uncertainty for the Muon G-2, and that will come between an introduction and the conclusion. And we discussed with Rishi that probably the most interest will be on hadronic vacuum polarization, so I will keep this part longer. But I hope to have some time to discuss hadronic light by light too. So let's start with that, and with this plot, which shows the history of G-2 measurements. They started in the 60s. You see with the huge error compared to later ones. This was the CERN experiment, which lasted about 20 years and reached a very good precision. I mean, increased the accuracy dramatically with respect to the very first measurement. But after that, they stopped, and then there was an almost 20 years hiatus between that and the next experiment, which was carried out at Brookhaven, and which produced several measurements. You can see, you can appreciate also the reduction on the error on this zoomed in part of the plot. And what you also see on this plot are some theory points. First of all, the purple point here, which is very far away from the G-2 measurements, from the Muon G-2 measurement, is the electron G-2, which, as you see, is very different, and as is well known. And then what you see, this downward pointing triangle, which is also very far away from the measured value of G-2, that is the G-2 of the Muon if you only take into account QED contributions. In other words, if you switch off strong interactions and weak interactions. And so you see that you need something else, something large, to be able to understand the measured value, and QED is not enough. Let me show you some numbers corresponding to these points. First of all, the world average at the end of the Brookhaven experiment shown here. And point out again in numbers that the bulk of the difference between the electron and the Muon G-2 is due to QED and arises from large logs of the ratio of the two lepton masses. The difference between the experimental value and the purely QED contribution to the Muon G-2 is about 7,000 in 10 to the minus 11 units. Hadronic contributions, if you try to estimate them quickly, you realize, and for that you essentially need to take into account the rho contribution, that they are of about this size. And so if you see a difference between experiment and the QED value, it means that you are seeing the hadronic contributions. And that was already the case at the end of the CERN experiment at the 5 sigma level. If you now estimate again, also at the level of order of magnitudes, the weak contributions, these are an order of magnitude, almost 2, smaller than the hadronic ones. So 150, 10 to the minus 11, and that's 2.5 times the experimental uncertainty at the end of the Brookhaven experiment. So it's for the weak contributions, the higher precision of the Brookhaven experiment was needed. Now, as you all know, Fermilab has shown the first of a series of measurements which they plan to do last April. That's the number, and so that makes the final average shown here. And this is a plot showing the Brookhaven value as this yellow band with the projected final Fermilab uncertainty, which you see is a factor 4 or smaller, and then some theory values for the total of G minus. So you see that on the scale, on the horizontal scale, 0 is set at the value of at the experimental value. So this is essentially a mu of the standard model minus the experimentally measured value. And here you see in the lower part of the plot two evaluation of hadronic vacuum polarization, which were combined in the value of the white paper, correspond to this black point and the gray band. And above this line, numbers which have not been used in the white paper, the average of the lattice result and the BMW result, which appeared at the same time as the Fermilab announcement. And this is a Jaeger linear result, which also did not.
People to join us. So welcome to this special edition of the GTI.
What is, okay. Now in this plot, you see the combination of Brookhaven and Fermilab with the well-known 4.2 sigma discrepancy, and all the rest is the same. And here on this plot now there are more theory numbers. This shows you that on the lattice there's a lot of activity going on, and the light blue band is the white paper summary of these results, which, as you see, have an uncertainty which is significantly larger than the data-driven ones. Here's a table summarizing the various numbers. First of all, if you look at the lower part of the table, I hope you can see my mouse, the arrow. You see the theory value, the experimental value, and their difference, these famous 4.2 sigmas. And the theory value is the sum of QED, electroweak, hadronic vacuum polarization, and hadronic light by light. Vacuum polarization known to leading, next to leading, and next to leading order, next to next to leading order, and hadronic light by light known at leading and next to leading order. And you see that the by far largest contribution is QED. The second largest contribution is hadronic vacuum polarization, and then of about the same size, electroweak and light by light. But if you look at the uncertainties, and don't get confused by these 3 digits given here, they all come after the comma. So that's a completely negligible uncertainty. The 2 main sources of uncertainties are hadronic ones, and hadronic vacuum polarization is at the moment the largest. And if in the upper part of the table, you can now see the breakdown of these 2 hadronic contributions in leading, next to leading, etc. The data-driven evaluation of hadronic vacuum polarization is shown in the first 3 entries. The lattice result for hadronic vacuum polarization, the average, the estimate given in the white paper is shown here. For hadronic light by light phenomenology, which has reached about 20% uncertainty, an estimate of the next to leading contribution, which is an order of magnitude smaller, as you would expect, and which was calculated because for hadronic vacuum polarization, the step from next to leading to next to leading, you see that the reduction is not so strong as one would have expected, and that is due to logarithms of masses, which play an important role. And it was important to check that the same kind of effects do not appear in hadronic light by light, and indeed this is not the case. Now for hadronic light by light, the lattice at the time of the white paper produced 1 result, RBC UK QCD, which was compatible with the data-driven estimate and which could be combined in the final number you see here. So although the uncertainty from the lattice is larger than the data-driven one, but the combination led to a somewhat reduced uncertainty. So that's the situation. And to add to that, we have to mention the BMW result, which, as I mentioned, came at the same time as the Fermilab announcement, with a larger estimate for hadronic vacuum polarization, and for the first time for a lattice calculation, an uncertainty which is compatible to the one obtained with the data-driven method. Now, the white paper I've mentioned already a number of times is this physics report here, which is, well, appeared in 2020 before the Fermilab announcement, and with about 140 authors and an initiative which was coordinated by this steering committee. And the work started in 2017 and is going on still, and will be going on as long as the experiments will be running, with the next meeting planned for September of this year in Edinburgh. Here's the summary, but I think I mentioned everything here, so let me move on and make the general comment that the theory uncertainty comes essentially from hadronic physics. The two contributions I mentioned, I depict here in this Feynman diagram with, so it's a vertex correction with a photon, but with the photon including a hadronic vacuum polarization. And the problem is then with hadronic physics is how to calculate this, because the scale here is a very low energy scale where strong interactions are non-perturbative. Now, in this case, one can rely on unitarity and analyticity, so essentially on dispersive approach, which gives you a direct relation of this contribution and experiment, the measurement of the cross-section plus or minus 2 hadrons. And there are a number of experiments. There's a history of many experiments which have measured this reaction, and some of them are active now and are planning to produce more results, more precise results. And as I mentioned, the alternative approach is the lattice, which is becoming competitive, and I will discuss this in more detail below. Hadronic light by light is one order higher. HVP is order alpha squared. Hadronic light by light is order alpha to the cubed. And so one expects this to be about a factor 100 smaller than hadronic vacuum polarization, as it is the case. And so while for hadronic vacuum polarization, you need an uncertainty below 1%, in this case, as I mentioned, this is now estimated to about 20%. This makes it subdominant with respect to the previous one. But this is the result of recent work, because earlier many people thought, or would even say publicly, that this could not be expressed in terms of measurable quantities, but now this has changed with the dispersive approach, which we have contributed developing in Bern, has led to a systematic treatment of this contribution too. And also on the lattice, this is significantly more complicated than hadronic vacuum polarization, but again here, it is becoming competitive, in particular thanks to the work of the Mainz group and RBC UK QCD. So let me now start with the hadronic vacuum polarization to discuss this in some more detail. So first of all, the quantity which we are interested in is the hadronic vacuum polarization, which is the two-point function of electromagnetic currents in QCD. Okay, and you see that this is a Lorentz tensor with two indices, but which can be written in this form because this can depend only on one momentum. And if it depends only on one momentum, then you can build two Lorentz structures. So in principle, you would have two scalar functions encoding the hadronic physics, but then gauge invariance tells you that the two structures have to appear in this combination. So in the end, because of gauge invariance, you you have only one hadronic scalar function. Now, it is important also to remark that here, this structure you can write in many different ways. You could multiply or divide by q squared or powers of it, and the expression would remain valid. However, only with this structure as written here, then you can say that the scalar function which multiplies it doesn't have neither singularities nor zeros, so that you can write a dispersion relation for it. And the dispersion relation is written here. All you need to know for this function is its discontinuity, its imaginary part on the real axis from 4 and pi squared up to infinity. Once you have this, you can reconstruct the whole function via this dispersive integral. Now, all this I mentioned is easy. In fact, it's usually not mentioned. These few steps you have to do to get to this point, to a dispersive treatment. But I mention it because you will see that for hadronic light by light, things are much more complicated. So now you have established this dispersion relation. Now the question is, what gives you the imaginary part? And here is where unitarity plays a role and tells you, it's essentially the optical theorem, that if you cut through this blob, then you get the imaginary part, but the imaginary part is given by the multiplication of these two amplitudes, which is essentially the modulus square of the sub-amplitude, let's say, on the left, which is the process E plus E minus, while a virtuous photon going to hadrons. And so virtual photon you can obtain with E plus E minus. And so the imaginary part is related to this cross-section. So analyticity we've mentioned. And now if you you see the momentum is the q square here, the momentum, the loop momentum. And so once you write this contribution in this way, all you have to do to calculate this one loop is to consider this, which is essentially a propagator, but with a variable mass s. Now this one loop you can calculate explicitly, and all what remains to be done to get the total is the integral over s. So in this way, you get this result with ks, a known function, because this one loop integral I mentioned with this propagator with variable mass can be calculated analytically. And now what one should remark about this expression is that you have a 1 over s, an explicit 1 over s times a known function, and this known function even goes to 0 for large s, like 1 over s. So overall, what multiplies the R ratio is a 1 over s squared. So it's clear that the lower part of this dispersive integral is the most important one. And once you have this formula, then all you need to do is to measure this R ratio as accurately as possible, combine the results of the various channels, the various energy region, and calculate this integral as accurately as possible. And that's the work which has been done over many years by different groups. And at the moment, there are essentially two main groups which are doing this complete calculation. This is the group of Davier with Höcker, Malescu, and Zhang, and Keshavarzi, Nomura, and Teubner. So these are the two main analyses which have been taken into account in the white paper. And if you look at the final line, you see that the two analyses agree very well on the total. They have a different estimate of the uncertainty, but the difference of 1.2 is lower than the uncertainties of either of the two. However, if you look at the details and at the individual channel, you soon realize that the situation is not as nice as it looks if you look only at the total. And in particular, for the main contribution, the 2 pion contribution, the difference is 3.6, in fact, of the order of the final total error of the collaboration, which has the largest error. And so this relatively large difference is then compensated, by other differences with opposite sign, which in the end combine to give you a total, very small difference. And so this fact, these differences in the individual channel has been addressed by the white paper, by the Muon G-2 theory initiative, because the goal was to get a conservative result, a consensus, but conservative result. And so much work went into trying clarifying these differences. And since the large contribution, you see, by far is the 2 pion contribution, and the reason is that there's this kernel which has this 1 over s squared, so the intermediate state with the lowest threshold is the one which counts more. So the 2 pion. So the 2 pion channel is the one where there's the largest difference, and it's in total the most important one. And so it is important to give a serious look at this one. And what these two analyses haven't done, but what one can done, is to take into account that if you consider the 2 pion contribution, this can be expressed in terms of another one hadronic amplitude, the scalar one, which is the vector form factor of the pion. So essentially this blob of the virtual photon going to 2 pions, not just any hadron, but just 2 pions. And to take into account that this quantity itself satisfies the dispersion relation. So essentially, if you consider this sub-amplitude and you cut through this blob, you have contribution from different intermediate states, 2 pion depicted here, 3 pion, 4 pion, etc. And you can write the dispersion relation also in this case, so you can express this total hadronic quantity, this form factor, in terms of its imaginary part. And in this case, Omnes has shown that you can end up with a mathematically exact formula, which tells you that if you know the phase of the form factor, you can reconstruct the whole form factor, assuming that you have no zeros in this form factor, which is what I will do. Now, what's is here in this integral, which then is the argument of the exponential, is the phase of the form factor. In the elastic region, the phase of the form factor coincides with the phase shift, with the pi-pi phase shift, with the quantum numbers isospin 1 and angular momentum 1. But then above the inelastic threshold, you have other contributions. And so you can split this total phase into the elastic pi-pi phase plus inelastic contribution. And since you have a sum here of 2 contributions, the integral is a linear operation. So you have the sum of 2 integrals, and the exponential of the sum of 2 objects gives you the product of 2 objects. So the product of 2 Omnes functions, one containing only the pi-pi phase and the other one the inelastic phase. And the inelastic phase is actually bounded with a bound which has been derived by Eidelman and Lukaszuk, which can be expressed here in terms of the cross-section E plus E minus going to any hadrons but the 2 pions. And what experimental data on this R, on this ratio here, show is that although the inelastic phase starts in principle at the 4 pion threshold, which is quite low, it is significantly different from 0. You start to see a deviation from 0 essentially at the pion pi plus omega threshold, which is much higher. So this channel takes up steam only if you have a resonance like the omega. This is important because then this contribution will be constrained quite strongly. So this is the contribution essentially of 2 pions. The inelastic phase gives you 4 pions and higher. But then you have also contribution due to 3 pions, and that's due to isospin breaking. And that's the phenomenon, the well-known phenomenon of rho omega mixing, which is expressed in terms of this function here, which contains Breit-Wigner for the omega. The omega is a very narrow resonance, so this is a very good approximation. We have even tested that the difference to a full treatment of the omega resonance doesn't change anything. And then you have a parameter epsilon, a small parameter, which is responsible for this isospin breaking effect, the mixing of these two resonances of different isospin. And this representation, which writes the form factor as a product of these three functions, is what we have used and to describe the data. And here you see a fit of the many data, which there are here, not all of them are represented, there are many more than this. And you see that with this representation, in these dispersive interval, you can take S time-like or the space-like, it doesn't matter. In this representation, you can fit at the same time with the same formula also space-like data, as shown here. And this plot shows you the contribution of the rho omega mixing. So it's a function which is essentially one everywhere. It becomes relatively large, a 10% correction, but only in a very narrow region, the one exactly around the omega mass. And this is the contribution, well, this is the phase, the inelastic phase, and you see that these points are the data for this Eidelman-Lukashuk bound, so the phase is allowed to be only within these two branches, the positive and the negative one of this data. And these are results of the fits we have done to different data sets imposing this constraint. And you see that the phase starts at the omega pi threshold, and it's constrained to be small, to remain below 10 degrees, even as you go up to 1.15. So this inelastic contribution, the omnes inelastic, is constrained to be smooth and small. The difference from one small if you go below 1 GeV. And here is a normalizer. Yes, please.
Can I ask a quick question about the previous plot?
Yeah.
I couldn't quite get this. So the different curves are different fits to different data, you said, right?
Yes.
Okay. They do seem to differ quite a bit. Is your statement that this dispersion in the fits does not contribute a lot with this phase shift that you're calculating? Is that the statement? Yes.
So you see this phase, I'm splitting the pi phase shift from the inelastic one. So the pi phase shift, here you have the rho at 0.7. So at energies of around 1 is above 100 and something in degrees. I don't know, maybe 120 under. And so you see that compared to the main contribution coming from pi, this inelastic one is tiny.
Okay.
And moreover, what I'm showing you here, is only the inelastic phase, but there will, for each of these curves, there will be an elastic phase which will be slightly different, so that this doesn't give you, is not representative of the real difference for the total form factor. I hope this is...
okay, thanks.
Yeah, so this plot shows the relative difference, and you see blue is Chloe and red Baba. You see the well-known systematic difference between the two, Chloe being lower than Baba. And here, a plot showing the contribution to G-2 if you use either of these data sets, those we have analyzed at the time. And again, you see the difference between Chloe and Baba, or what you get if you combine everything. which is divided here.
Gilberto, Anand has a question. Go ahead, Anand.
Go ahead, Anand.
Yeah, sorry for interrupting, but I have to go out for a few minutes and rejoin. One of the questions that I wanted to ask you is, even if you took into account all these differences between the various HVP fits, either those of yours or those of K and T and so on, there is no way that these can ever account for the huge difference between the full theory result and the full experimental result, no? So, right. Would you have a comment on that?
I think a plot later will make this very clear. So let's come back to this later, in particular when I will compare to the lattice.
Okay, yeah. I will rejoin around then in about 25 minutes.
Okay.
Okay, thanks. Bye.
So now, after this digression on the 2 pi contribution, which, let me emphasize, is the most important one, but not the only one, here I'm showing you a comparison between these 2 analyses, which did not make use of any of this theory. They did not do fits to data. They just took the data as they are. So doing sort of trapezoidal rule, calculating the integral by trapezoidal rule. Now we did, when writing the white paper, a comparison energy bin by energy bin between this dispersive approach, and here's the work also of Anand together with Irinel Caprini and Das, which concerns only the region below 0.63, and you see that there's very nice agreement with our dispersive analysis. But the comparison between the dispersive approach and the purely data-based has led to an improvement and a clarification of some of the differences here. Now, let me come to the conclusion, to the combination of these results, and in particular to the protocol which has been adopted by the white paper. So the 3 points are written here. Central values are obtained by simple averages, channel by channel, and mass range by mass range. The largest experimental and systematic uncertainty of these 2 analyses was taken. And whenever there was a significant difference between the 2 analyses, or in the 2 pi channel between Babar and Chloe, half of this difference was added to the total uncertainty, so that the final result is written here. And you see that this last step, so first of all, that the larger systematic uncertainty was taken, and then that a difference between different analyses was added to the systematic uncertainty. This makes this large contribution to the uncertainty as large as the purely experimental uncertainty, and leads to the combining these 2 in quadrature to this 4 in 10 to the minus 10 units uncertainty. Let me now come to the lattice and briefly discuss the method. So the object one has to calculate is again the 2-point function on the lattice would be calculated as a correlator of these 2 operators with the Euclidean momentum Q. And so if you want to calculate now the contribution to A mu, you have to calculate this scalar function here for Euclidean or space-like momenta, and integrate with this kernel function. If you use this method, the disadvantage is that the integrand is peaked near q squared equal the muon mass squared. Here, the difference with respect to the previous formula is that the other one concerned time-like values of the integrand, and here, sorry, of the integration variable, and here we are talking about space-like values. And so for space-like value, the integrand is peaked near m mu squared. So in order to do this calculation accurately, one needs many points at small momenta. And this, on the lattice, requires large volumes or twisted boundary conditions. This is very well illustrated by this plot by the Mainz group, you see that the energy region here is shown from 0 to above 2.5, and here it's shown how much they contribute to the total of G minus 2. And the region 1 up to the muon mass squared is invisible on this plot. And in this region, there are no lattice points. So a quarter of the contribution is essentially inaccessible. The largest contribution is from region 2, which is up to 0.2 GeV squared. And here, with twisted boundary condition, you can put of the order of 6 points, at least at the time of this calculation here. And the many points you can have in this is in this broad region 3, which, however, contributes very little. So that's the difficulty of doing a lattice calculation for this quantity. But there's another approach which has been developed by Bernecker and Mayer, the so-called time momentum representation. You do the integral, not the Fourier transform, just the integral over space of this correlator. So this is now a function of time. And they have calculated the kernel's function, which you have to use to integrate over time for this time-dependent correlator to get the contribution to G mu. The disadvantage of this method is that the noise grows very fast with t. And here's a plot. You see the contribution as a function of time with an estimate of this correlator. See, it's peaked around 1 Fermi for time. But the point is that the contribution of the tail is not small, but as soon as you go up to 2 Fermi or so, the noise becomes significant. And so the risk is the problem is to get a large uncertainty from this region, even if it contributes not much to the total. That's the approach which BMW has used to calculate this quantity. And they did the state-of-the-art calculation with a 4 Fermi lattice. They even used an 11 Fermi lattice for finite volume corrections. And they did it essentially with physical quark mass and included all isospin breaking effects. And this is shown by this plot here taken from their publication on Nature. The upper row shows the diagram in the isospin limit with a light quark contribution, strange contribution, charm, and even a disconnected one. This all in the isospin limit. And then all the others are isospin breaking effects, either QED or strong. And if you look at the numbers here, you see that all these isospin breaking effects are small, but they are very expensive to calculate on the lattice. So this is where all the work, or much of the work, went into. On this plot, you also see the estimate of finite size effects. Finite volume effects are important here, and you see that they contribute almost 20 units to the total, with the final uncertainty, which is a factor 4 smaller. And so it was important to calculate these finite size effects precisely, and that certainly was one of the successes of this calculation. The final result is shown here. What is not shown here, but rather in this plot, is another important systematic effect on lattice calculation, which is the continuum limit, the lattice size effect. Of course, on the lattice, you can only do calculation with a finite lattice spacing, and then you have to extrapolate to lattice spacing equal to 0. And here you see that in this work, they have then corrected the lattice spacing dependence in different ways and done the extrapolation then in different ways after applying these corrections. And so they got a certain distribution of possible extrapolation to the continuum limit. And the distributions the distribution of these are shown by this histogram. And in the end, the final result, or the final uncertainty, is shown by this purple with the larger one, systematic effects by the gray band. And to give you, and this is essentially the main contribution to this 5 units of systematic uncertainty, but to give you a better idea of the importance of this effect, here's a plot showing the raw data without corrections. And you see that the extrapolation in this case would have been, first of all, different and significantly more uncertain because much dependence here is much steeper. And let me finally show this plot, which shows the so-called window quantity. Again, the continuum extrapolation for the window quantity, and the window quantity is obtained by integrating in time, not with the weight function which has been calculated and which I showed you before, but splitting the integral in 3 pieces by multiplying the integrand by 3 different weight functions whose sum gives exactly 1. And these 3 weight functions are shown here. Okay, so the window quantity is the one obtained with the black weight function. And you see it gives a total which is much lower than the final. But because of this weight function, this quantity is easier to calculate than the total. And so although BMW is the only lattice collaboration which has done a complete calculation with such a precision for the window quantity, there are several other lattice calculations of a comparable precision. And the problem which this plot shows is that the BMW result agrees well with another lattice calculation of similar precision for this quantity, but disagrees with a third lattice calculation of this quantity, which also has a similar precision for this quantity. And the purple point here is what you get if you do the integral over the E plus E minus data with a weight function which corresponds is the translation of this weight function in time into a weight function over S. And so using this weight function, you can now do the integral with the data, and you end up with this point here, which agrees with this lattice calculation, but disagrees again with the BMW. And here's a plot from stolen from Davide Giusti, who gave a talk at the Lattice conference last summer. And this shows that there are now several other lattice collaborations which have calculated these quantities. This the leftmost plot you see down here. And you see that there's a distribution of values from lattice collaboration, many of them with very high precision. And so this shows that the situation needs to be clarified among different lattice collaboration before one can talk about a problem or a discrepancy between lattice and data-driven approach. But let us now discuss what are the consequences of this BMW result if one takes it at face value. First of all, a shift in the value of G-2 from hadronic vacuum polarization, since the relation to the E plus E minus cross section is exact, a shift in the value of A mu must come from a shift in the cross section with respect to the data which have been used to calculate them. So somewhere the data must be wrong or a shift is needed. Now the running of alpha electromagnetic at mz squared is determined by an integral of the same cross section. And so if you have a shift of A mu, and this implies a shift in the cross section, the shift in the cross section will imply also a shift in the running of alpha. Okay, now if you make a shift in the running of alpha, there is an impact on the electroweak fit, which is precise and delicate. And 3 different analyses have shown that if you take the BMW at face value and make hypothesis about where the shift in the cross-section, in which kinematic region this has to happen, and then you analyze the impact on the electroweak fit, all the three analyses concluded that the shift in the cross-section has to occur below 1 or really maximally 2 GeV. Okay, otherwise you create a problem with the electroweak fit, and then it means that you need to find BSM physics, which explains that. Now, if you change the cross-section below 1 GeV, it means essentially you have to change the pi-pi channel. And so, together with Martin Hofericht and Peter Stoffel, we have analyzed this scenario in some detail, in particular because we have this dispersive representation of the 2 pion contribution. So we have allowed the parameters in our parameterization, the elastic phase, the inelastic one, etc., to be shifted to explain the difference to BMW. So we have done the fit to the data, but requiring that the total for the integral gives you BMW instead of being what it is. And so you see that the black curve here is the one fitting the data, and the other curves, the dashed green and black or the dotted red, they are what you get if you require that the integral agrees with BMW. And so you see that you end up in disagreement with the data, and you can end up in flat disagreement with the data if you require that it's only the pi-pi phase shift which are changed. You get a better result if you allow the inelastic phase to be changed. And here's a plot showing you how much the chi-square has to change if you want to move from the minimum of the fit to a value which agrees with the BMW. So it would be an enormous shift in chi-square. And this is the plot which shows you the correlation between A mu and the running of alpha. So you see that if you move from the minimum of the fit, which corresponds to about 495, to the value of BMW, you necessarily have to shift delta alpha. And this correlation is essentially independent on what parameters you allow to change. And you see that you have an increase in this running of alpha of about 1.5 units. So this number here would have to be increased by 1.5 units. So you see there's a slight tension with the electroweak fit, and this tension would become larger, even if you allow the cross-section to change only below 1 GeV. Let me skip this point, which shows the correlation also with the vector radius of the pion. And here's a plot which I think Anant wanted to see or refer to. So here are the various the results obtained by doing the fit to different data sets. And this is a comparison to what you would obtain from the lattice integrating only below 1 GeV. Well, assuming that all the rest is in agreement with the data-driven approach, then I'm subtracting the total contribution from above 1 GeV obtained with the data-driven approach, which is this 197.7 units. And so you see that BMW and the result, the experimental result, would be at the end of the bar for the error bar for BMW, so essentially here. So as Anant was saying, no difference between different data sets can possibly compensate the difference with the experiment. But now the point I want to make on this plot is, first of all, that BMW, if you look only at the region below 1 GeV, touches with Wabar. So it's not a dramatic difference. It's significantly different from Chloe, but okay, there is this problem between Chloe and Wabar. But the point is that if you take into account this window quantity, okay, and you see that for the window quantity, there remains a difference with what you obtain by calculating this quantity with the R ratio. What we concluded, okay, from this comparison here, is that part of the difference, because you know, if we had assumed that, no, if you assume that all the difference is below 1 GeV, then you calculate this window quantity with the shifted cross-section as we have obtained. With the shifted cross-section below 1 GeV, we would have to obtain for the R ratio result for the window quantity something in agreement with the BMW result. But this was not the case. So this means that part of the difference must come from above 1 GeV. And in fact, we estimated with Martin Richter and Peter Stoffer that at least 5 10⁻⁻10 units of the total of 15 or 14 of difference have to come from above 1 GeV, which means that instead of subtracting this 197.7, you have to subtract 5 units more. And so in this case, then the BMW result comes closer to the experimental determination of this contribution up to 1 GeV. So in this case, there is in fact a very good agreement with the SND and Babar, and the problem difference is with Chloe and Bess 3. But then there is the problem of how to explain the difference from above 1 GeV and the impact this would have on the electroweak fit. So do I have another 5 minutes?
Yeah, certainly. Yeah, no doubt at all. Yeah, sure. Yeah.
Let me discuss a bit quickly the hadronic light-by-light contribution. So in this case, you have 4-point function of the electromagnetic currents in QCD, calculated until some years ago only with models, but then a data-driven approach has been developed and used. Let me skip this part and come to the dispersive approach. So the problem here, making the comparison to the discussion I made for hadronic vacuum polarization, the 2-point function, here with a 4-point function, you now have 3 independent momenta. And in order to build a tensor with 4 indices with 3 independent momenta, you have many more possibilities. And in fact, you can find out that you need 138 different Lorentz structures. You can build 138 different Lorentz structures. In 4 dimensions, only 136 are independent. Now, this is the step which for hadronic vacuum polarization would have given you only 2 independent functions. Then gauge invariance reduces the number to 1. In this case, from 136, you have to impose gauge invariance, and you come down to 443 basis tensors. But then there's the issue of Tarrach, that you need 11 additional ones to have a complete basis everywhere. And so you end up with a total of 54 structures, but only 7 are distinct. Then by crossing, you obtain all the others. In other words, the corresponding decomposition to one of hadronic vacuum polarization is written here, and you have 54 different structures to take into account. Now you can try and do the integral with these 54 structures, the 2-loop integral, which is shown here, okay, with the tensor structures you have written. And part of these integrals you can evaluate. You have a 2-loop integral, so in total you have an 8-dimensional integral, and 5 of these integration you can carry out explicitly even without knowing these functions, because they, as being scalars, they depend only on the independent scalars, and so you can do all the other integrals. So the final formula is shown here, what we define as the master formula for hadronic light-by-light, and which expresses its contribution in terms of a triple integral with T known kernel functions. And this PI now you can evaluate dispersively. Now, evaluate these dispersively is complicated, but work in this direction has been done. And in particular, for the first 3 lines, lines in this table, which contain the most important contribution, the dispersive approach has led to significant improvements. In particular, the pion, the pseudoscalar poles are now known with about 4% uncertainty. The pion box is known to a 1% uncertainty, and the S-wave rescattering, the 2 pion S-wave rescattering, is also known to a good uncertainty. It's a smaller contribution, so this about 20%, no, 15% uncertainty is very acceptable. So if you combine this largest contribution, you obtain 69 as a result, but in particular, you obtain a reduction of the uncertainty with respect to earlier analysis, which is very significant. And here is where you see the power of this dispersive approach. These other contributions, which are somewhat higher in energy, they weigh less, they have less weight in the total, and so they contribute less. These contributions, for technical reasons, which I don't want to get into for reasons of time now, for these we could not apply to its full scope this dispersive approach, and so we have somewhat improved the estimate, but not nearly as effectively as for the first 3 entries. Moreover, in the total, we have added these generous uncertainties in linearly, so that in the end, we obtain a 20% uncertainty, which makes it subdominant with respect to HVP, but now, so with respect to earlier estimate, it doesn't look as impressive. Let me show it here on this plot. This is the data-driven result I just discussed. There is the result by RBC UKQCD, which have been, these two have been combined in the white paper, giving this black point here. And after, or at the same time as the Fermilab announcement, after publication of the white paper, Mainz also gave a result for this quantity in very good agreement with the others. And here you see the earlier ones, which just are in the right ballpark in agreement with the latest calculation, but with larger uncertainties. Let me skip the most recent result and let me come to the conclusion. So I have discussed the white paper, which provides the current status of the standard model evaluation of the G-2 and pointed out this 4.2 sigma discrepancy with the experiment. The evaluation of the hadronic vacuum polarization contribution, the data-driven one, has reached a 0.6 error. And this is now the largest source of the theory uncertainty. The BMW calculation has, for the first time, obtained the result from the lattice with a similar precision. And unfortunately, this differs from the dispersive one. Now, if the BMW result were the correct answer, the discrepancy with the experiment would come down to below 2 sigma, would change the picture completely. However, this discrepancy with the dispersive evaluation has to be understood. Hadronic light by light contribution has been calculated based on dispersive approach with an uncertainty of 20% accuracy. And 2 recent lattice calculations have confirmed it. Now, what will come in the future? First of all, the Fermilab experiment will further reduce the Brookhaven uncertainty by a factor 4. So this might lead potentially to a 7 sigma discrepancy. And this, of course, has to be matched by more work on the theory side, the data-driven side, in particular HVP. Other experiments are already available, came out after the publication of the white paper, or are forthcoming, and this will lead to an error reduction. Moreover, the Muon E experiment at CERN, analyzing mu E scattering, so a T-channel photon exchange, and they want to extract the vacuum polarization from T-channel, so in the space-like region, aims to provide an alternative measure of hadronic vacuum polarization. On the lattice, very important that more calculations come out with the same precision as BMW, and the difference to data-driven evaluation has to be understood for hadronic light by light, the data-driven approach has the potential to reach a 10% uncertainty within a couple of years. And on the lattice, also, I think they can improve and reach something like a 10% uncertainty, and then combining these results, hoping that they will agree, will lead to further improvement. Let me close with this picture of the experiment which is planned at J-Park, which hopefully will provide an alternative way to measure the Muon g-2. Thank you very much for your attention.
Thank you, Gilberto. Please go ahead if you have any questions. So Anant is here. Okay.
Yeah. So basically, to the same question that I was going to ask again, that the relative differences between various HVP fits is actually below the kind of noise that you're looking at, no? So I was just interested in knowing what possible improvement can there be, because the elephant in the room is experiment versus theory or BMW versus experiment. Within the experiment, what possible room is there for improvement is my main question.
Well, difficult to say. So first of all, this is the picture I was referring to. You see the different contributions from below 1 GeV obtained with the different experiments, and the experimental point is essentially at the end of the BMW bar. Okay, so it's somewhere above 515. So as you said, the difference between the experiments cannot possibly explain this. This difference here. Now, we know what will come. Okay, Chloe will not change. Babar is working on a new analysis, or there are data which they have on tape which haven't been analyzed, and they are working on the analysis of these. And so there will be a new number from Babar. Of course, this will be very interesting. BESS 3 is shown here. This is rather on the low side, rather in agreement with Chloe, but with still a large uncertainty, they can improve. And SND has come out already with new numbers that our fits with the dispersive approach are not so good as for the other experiments. So there's something we need to understand. And then there is a measurement done by CMD3. So this is what will come, and then we'll have to see how the situation looks like once these new measurements have come out.
Thank you.